Simple harmonic motion is a special case of what falls under the category of oscillations within physics. So, simple harmonic motion describes oscillations that are not damped. In reality, most oscillations are damped. In other words, they don't keep going forever. So, for example, if I hang a mass from a spring and I pull it slightly, the spring will wind up bouncing up and down. And it turns out if it's a good spring, it could actually do that for a while. It could do that for a matter of minutes, maybe even tens of minutes before the oscillation dies away. Harmonic motion, mathematically, though, does not die away. So again, that's something that we don't necessarily see a mass on a spring do ordinarily. But one could argue there are actually things like microscopically, even you could argue that electrons within atoms are doing something a little bit analogous to a harmonic motion that never really goes away. So this is actually something that's connected to a lot of things in our reality. But we're going to study it. In this topic, we're taking a kind of mathematical approach to what we're describing as harmonic motion, or sometimes it's also called simple harmonic motion. I have a function here on the key concept slide. X of t is equal to a sine omega t. So that thing that looks like a W is omega. We've seen omega before as either an angular velocity or maybe angular frequency when we looked at rotations. In this case, it really is just an angular frequency. There's nothing really rotating in harmonic motion, so angular frequency is the more appropriate term, but the same symbol is used. F is the ordinary frequency, so when you look at the formulas here on the key concept slide, we got omega is equal to 2 pi f, and we also have that f is equal to 1 over t, while t is the period. So these are some simple formulas that are good to know, simple relationships between these different parameters that describe harmonic motion. The angular frequency is the parameter that looks the simplest when you express harmonic motion as a function. And so I've written here on the whiteboard to demonstrate that. The basic function, again, is a sine omega t. If you use the formula for omega is equal to 2 pi f, that shows you what that function might look like when f is plugged in. You know, a question that has come up sometimes in the past that's a matter of notation is, for these functions, is should I regard the t as being inside the sine function or outside the sine function? Really, for all of these, there is an implied set of parentheses, and I'm going to go ahead and make explicit right now. So in other words, all of this is inside the sine function, and as you can see, when I switch to using ordinary frequency instead of angular frequency, what's inside the sine function gets more complicated. And over here, if you do it in terms of the period, it looks a little bit different and is also a little bit complicated. So the utility of the angular frequency as a symbol and a quantity that's defined is in part that it's the simplest thing to describe mathematically. You can think of it, though, I mean, if you think about like the analogy between this and rotational motion, we saw there that the frequency at which something rotates could be thought of as like revolutions per second, perhaps, and then omega describes radians per second, and since there's 2 pi radians in a revolution, that's kind of a way of thinking about this formula, and that thinking still pretty much works here, even though we're not describing rotations. The deep connection that is there, though, between rotations and oscillation is when something is rotating, it turns out the components of motion are actually oscillations or simple harmonic motion. That is, in other words, if an object is moving in a circle, say in a vertical plane, there would be a horizontal component of motion and a vertical component of motion, and those would each be described as simple harmonic motion. The last formula I have here on the key concepts page is one we're going to look at in an example, and it says that the maximum velocity in simple harmonic motion is equal to the amplitude times the angular frequency. And we're going to look at where that comes from, and then that turns out is going to be useful to us when we start to look at physical examples of simple harmonic motion.